What's up, guys? My name is Ritvik, and today I'm here to teach you everything that you need to know for AP Physics C Mechanics Unit 3. And before I begin, if you haven't already, please go to the description right now and get my free AP Physics C Mechanics book, because that book has everything that you need to know to get a 5 and an A in your class. So what are you waiting for? Get it right now, and now let's immediately begin with this unit. So this unit begins with some basics: systems and forces. So a system is a group of objects that we specifically look at in a problem. And an internal force is a force that occurs between objects part of that system, while an external force is a force caused by something not part of that system. So now let's move on to work and power. So work is basically the transfer of energy that is caused by a force that acts on an object. So when I said external force on this slide, I mean applied force, right? Some sort of applied force. Maybe you're applying the force, maybe friction is applying the force. For example, friction can also do work. The force you apply, that can also do work. And then in general, work is force times displacement times the cosine of theta, where theta is the angle between the force and the displacement vectors. And then remember that only the component of force that is parallel to the displacement vector, only that component can do work. And then power is the rate at which work is done. And to find power, you simply divide time from work, and that's your average power. So now I have a few conceptual questions for you. What is the area under a force displacement curve? Well, the answer is work done. The area under a force displacement curve is the work done. Now I have another conceptual question for you. In uniform circular motion, what is the net work done? What is the work done by the forces? Well, the answer is 0. And the reason is that the force and the velocity vectors, they are perpendicular to each other. So since force and velocity vectors are perpendicular to each other, that means the work done will be 0. Now there's 3 main forms of energy that you will be dealing with. First is kinetic energy, which is the energy of motion, and the formula is 1/2 mv squared. Now for potential energy, there are 2 types: gravitational potential energy and spring potential energy. And gravitational potential energy is caused by the location of some object in a gravitational field. Now spring potential energy is due to the stretch or compression of some elastic object, such as a spring, and the formula is 1/2 k, where k is the spring constant, times x squared, where x is the displacement. Now the work energy theorem says that the net work done is simply the change in the kinetic energy. So that means 1/2 times m times the final velocity squared, minus 1/2 times m times the initial velocity squared. That's the net work done. Now mechanical energy. Now whenever you're asked to find the mechanical energy, you only add the kinetic and potential energies, both spring and gravitational potential energies. Now this is important because if they ask you to find the total energy, then that's different, because that can include stuff like friction. And also note that mechanical energy is known as the energy that can do work. And when no work is done on a system, then the energy will be conserved. And that brings us to the conservation of energy theorem. Now the conservation of energy theorem says that energy will be conserved when no external force does work on the system. So that means if that's the situation, then the initial kinetic energy plus initial potential energy equals to final kinetic energy plus final potential energy. Now conservative and non-conservative forces. So a conservative force is about doing work when the path of the object is negligible. However, for a non-conservative force, the path of the object matters. And this means that the path of the object, right, will affect the work done. So conservative forces include the gravitational force, which does not depend on the path, and the spring force, while non-conservative forces include friction, tension, and air resistance. Now for conservative forces, you can use the formula below that I've written on the screen to find the change in potential energy. It's simply the integral of the force, right? If you're given an expression for the force, then you can integrate that. And then the minus of that, that's going to be the change in the potential energy. Now using the same formula above, we can find that minus du over dx equals to the force. And this is important because sometimes you'll be given a potential energy curve with respect to x. And then if you find the slope of that curve at a point, then you can find the force of it. Now non-ideal springs. Now for a linear spring, the force was equal to minus kx, which was also the Hooke's law. However, for non-linear spring, the force will not be equal to kx. It's going to be a complicated expression. Now, if you want to find the potential energy for a nonlinear spring, you simply integrate the force and use the formula that you can see on the screen. Now, this is important because for a linear spring, the potential energy is 1/2 kx squared, but that's not true for a nonlinear spring. Now, there's another really important way to write power. Now, we know that power is work over time. However, we know that work is force times displacement times the cosine of theta. And now we have displacement and time. So if we divide both, we know that's velocity. So this can also be written as force times velocity times cosine of theta. Now let's look at a free response question from the actual AP exam. So please pause the video and try the problem on your own before proceeding. Now in this problem, there's basically this 100 kilogram box and it's being pulled by a person. Now we're given an expression for the position of this block. And the position of this block is 0.5 t cubed plus 2t. Now in part A, we want to determine the speed of this block at time t equals to 0. Well, we're given an expression for the position, and we know that velocity is simply the derivative of position with respect to time, which means v equals to dx over dt. So we differentiate our expression, and we can use the power rule to get 1.5 t squared plus 2. And now we substitute in 0 to find the velocity at time t equals to 0, and doing so gives us 2 meters per second. Now in BI, right, part BI, we want to find the kinetic energy of this box. Well, kinetic energy, the formula for that is 1/2 mv squared. And now to find an expression for the kinetic energy, we substitute our mass, which is 100, and we substitute our expression for velocity, which is 1.5 t squared plus 2. So now we can simplify this expression to get 50 times 1.5 t squared plus 2 squared. Now in the second subpart of part B, we want to find an expression for the force. The net force is mass times acceleration. And we know that acceleration is the derivative of velocity with respect to time. And we already have an expression for velocity, so we simply differentiate that. So differentiating 1.5 t squared plus 2 gives us 3t, which is the acceleration. And we know that the mass is 100, and now the acceleration is 3t. We multiply both to get 300t for the answer. Now in subpart 3 of part B, we want to find an expression for power. Well, we already have an expression for both velocity and force. So what do? Well, we simply multiply both of these expressions to each other to get 300t times 1.5 t squared plus 2. And simplifying this gives 450t cubed plus 600t. Now in part C, we want to find the net work done on the box. Well, we know that the net work done is simply the change in the kinetic energy, and this is the work energy theorem. So, now to find the change in the kinetic energy, we want to find the final velocity and the initial velocity. Well, we already found an expression for velocity. It was 1.5 t squared plus 2. So we substitute in 2 for the time to find the final velocity at 2 seconds. And we get that it's 8 meters per second. And now we can substitute in 0 into our expression for velocity to find that the initial velocity is 2 meters per second. So now we do 1/2 times 100 times 8 squared minus 1/2 times 100 times 2 squared. And we can simplify this to get 3000 joules, which is the net work done. Now in part D, we are asked, is the work done by the student greater than the net work done? Well, let's think about this. We know that the student applies a force. However, there's another force, friction force, and that's going to oppose this force. The net work done is simply the work done by the person minus the work done by the friction force. This means that the work done by the person must be greater than the work done by the friction to create the net work done. Now thank you so much for watching this video, and please don't forget to like, share, and subscribe, since that's going to tell me that you guys are truly enjoying and learning from the books and the videos that I've been making for you guys. And don't forget to join the Discord server to meet other hardworking students that are preparing for various competitions and exams such as the AP exams. And also, don't forget to follow the Instagram if you have Instagram to view educational reels and cool animations. And again, thank you so much for watching this video, and I really hope to see you soon back again on this channel.